So everybody likes a good Venn diagram during a presentation, but this is kind of how we think of the world of our tile system. So we need that big the production capacity from those field tiles. We always think that field tiles can pay for themselves, maybe get up a 30% yield bump from pattern tiling a field out, but we know that there can be some environmental consequences. So we're trying to find that nice overlap between those two, where we're getting that production value, but we're doing it in an environmentally responsible way. A lot of people in Iowa are very familiar with the Iowa nutrient reduction strategy. Looking at the nutrient reduction strategies from the other states in the Midwest, I would say Iowa probably does have the strongest strategy that's out there. It was one of the first strategies that was out there too, and so I think it's a big compliment to the state for what they did. But when we look at those practices and that strategy, we know that we're not going to get to that 41% nitrate reduction just from fine-tuning our infield management practices. And the reason for that is, if we look at this graph right here, and this was developed by Dr. Mike Castellano up there at Iowa State University. But this red line represents the organic nitrogen that gets produced from our soil, and the green line represents when our crop or corn or soybean systems are using that nitrogen. So you can see those two peaks don't line up. So we have this peak in early spring, moving into late spring into the summer, where we have that peak amount of nitrogen getting converted from that organic nitrogen to a mineral nitrogen. But unfortunately, our crops aren't using that nitrogen at that point in time. So we have a lot of room for that nitrogen to move down into the system, especially in these tile systems, and get out before our corn and soybeans can use that. So that really stresses the purpose of needing some structural practices out there to address these nutrient concerns. Cover crops can do a really good job. They build soil health. The cover crops are really only active until about right here before we have to burn them down, then again in the fall. So even the cover crops aren't going to meet all those demands. Also, another reason why we need to really manage our drainage water systems, this is developed by ISU economist Chad Hart there. But, if we look at our reasons for loss in our production systems, a lot of it stems from moisture issues, either too much moisture or not enough of these droughts. All these CCAs here, you do a really good job at managing for plant disease and insect pressures, and that's why those losses aren't nearly as big. But there's still a lot of room for improvement to manage our water, either by needing to drain it off that landscape faster with excessive moisture, or maybe slowing it down and holding it for times of year where we're going to be operating at a water deficient time in July and August, so during those droughtier seasons. So with that, the conservation drainage practices that I'm going to speak about today are really more we're talking about the single fields, not the larger watershed scale type practices. So drainage water management, bioreactors, saturated buffers, and multi-purpose oxbows. Wetlands are not another form of conservation drainage practices, but those are a little bit larger scale. Where we're, with the CREP wetland program, we're treating 500 to 2,000 acres. So I wasn't going to speak about that today, but they do great things as well for removing that nitrogen from that subsurface drainage. So first of all, I'd like to just point out some of the really good online resources that are available to everybody before I lose people by the end of the hour here. But if you're looking to get more information on these conservation drainage practices, here's a few websites that I really recommend people go visit. First, 4R Plus, we heard a little bit about that in the previous session, but that is a really nice, well-organized website. There are those CCA courses available on it. They are nice. The conservation drainage one, I think, took me about 15 minutes to watch the PowerPoint presentation all the way to the end. It's probably a 15-minute summary of what I'm going to talk about today in an hour. But then there's also a quiz at the end. I did get 10 out of 10 on it, so I was a little nervous if I wasn't going to pass that one. Another really good resource that's out there is transformingdrainage.org. And so that's a group of the extension universities in the Midwest that deal a lot with drainage. So your Purdue's, Iowa State, Minnesota, University of Illinois. They have this Transforming Drainage project where they go through and they talk about a lot of these practices, as well as some more innovative ones. One practice that they're really going to start pushing in the next couple years is drainage water recycling. We're actually looking at using that tile water, but then digging down a pond or a reservoir of sorts, and then being able to irrigate back out of that reservoir back into the field. So we can use some of that water, again, during those droughtier times of the season, in July and August, when we're operating usually at a water deficit with our systems. And also, the Soil Water Conservation Society just launched this late last fall, but it's a conservation media library, and that is an excellent source. It's all open source, so they don't mind if you go in there and take some of their information. But they have PowerPoints on all these practices that are available. They have Flickr accounts on there, so you can see them, practices being installed. I actually used quite a few photos from that for my presentation today, just because it is such a good resource. They also have video presentations describing the practice. But it's a really good way to familiarize yourself with some of these practices. And they have more than just the edge of field practices in there. They have the cover crops, prairie strips, and some of the common practices that you may have heard about. Finally, our website, I almost didn't put it on there. We're constructing a new website. The old website's pretty out of date when I came on board, so we're hoping to launch a new website in the next month or two, but that will, again, be an excellent resource to try to find some of these drainage water management practices. So first of all, drainage water management. We think of our typical tile system, so we just outlet it to the stream. Drainage water management, all that is what if we can control that outlet? So we don't need to drain water year round. Right now, a lot of tile lines might be flowing still from the previous fall. They haven't frozen down all the way, but we don't really need to be letting that water out. And so if we can control that outlet and prevent that water from flowing, then we can prevent those nutrients from making it into the stream at the same time. Also, if it allows you to control that water and maybe get some water back up into that soil profile and be available to those root zones later in the season, there could be a potential for yield increases if we can do that. So when we think about drainage water management, it is a management system, so we do need to go out there and manage these stop boards in place, because obviously we're not going to have that water held back year round. That tile system's in there for a reason. But there's really about 4 different settings that they can have it. Winter, you can be pretty aggressive and really stack those stop boards up, prevent that water from flowing out that outlet. Your spring operations, so about mid-March, before you're thinking about getting out there, I recommend pulling those stop boards down. If it's a conventional new tile system, they should be able to recover within about a week of pulling those stop boards to act like you never held that water back in the first place. So it should be able to drain all that winter water out if needed. And then in summertime, if that water's still there, you can go back and you can start backing it up and have it below that root zone still, but that way the roots can still go down there, but you're releasing a lower percentage of that water. In fall, if you still have water left in the system, a lot of times in Iowa, our tile lines don't actually flow during the harvest. This past year, that wasn't the case, but you can pull the stop logs just so you don't have any concerns about delaying harvest, and especially with your heavier equipment that are out there during that time. The big thing with drainage water management is it's very site-specific, so it's better suited on field areas with slopes of less than 1%. 0.5% is probably even better. That doesn't mean the whole field. If you have an 80-acre field, it doesn't mean that whole 80 acres has to be within that window. But if you have management zones at least 10 to 20 acres in size that meet that flat requirement, that's probably where they would be best suited. Looking at the cost differential from doing just your typical pattern tiling system versus controlled drainage, it probably will increase your cost from anywhere from $20 to about $90 per acre, just depending on how large those management zones are. Again, if you're only controlling 5 acres at a time with a controlled structure, that's probably not the best situation, probably not the most economical. But if you're getting into those larger systems, you're getting up to 20 plus acres controlled with a control structure, that's when we have those lower costs per acre come into play. This is a cost shareable practice through NRCS EQIP, and so there's a handful of different conservation practice standards that drainage water management would work in. And so the first one is just the drainage water management itself. They have a separate conservation practice just for these control structures right here. Also, They do pay for some of the tiling system that's associated with drainage water management, so sometimes with the design of these, you need a sub-main that probably wouldn't have needed to be there in a conventional system to help control that water. And so there's cost share available for those sub-mains if you have to put in additional sub-mains with that plan. Then also there's a drainage water management plan itself, so CAP 130. We heard a little bit about some of the other CAP programs in the previous presentation. To actually write that management of how to handle those stop logs throughout the season, there is some funding available for TSPs to help their clients with that. This picture here is just them dropping one of those control structures down into the tile line. So inside this control structure, that's where you'd have your stop boards that you can pull in and out throughout the season. Also, the next kind of step in this drainage water management is trying to automate these control structures. We know that farmers aren't going to go out there and pull stop boards on 5 or 6 different structures in their fields probably throughout the year. So what happens is they might get out there, manage it for the first season or two, and then maybe just forget about it and just leave them wide open. So if we can automate these things so you can control it from your tablet, change the stop log settings when you need to, that's going to be very beneficial. The technology is there right now. We're just trying to figure out ways to pay for it. You would need a cellular data plan for each one of those control structures, so you can communicate back and forth. If anybody has any questions during this, feel free to stop me and go ahead and ask. But the water quality benefits that we see from drainage water management is a 33% nitrate reduction. That's what's in the nutrient reduction strategy. We've also seen some very good phosphorus reduction numbers from these, and actually a little bit higher than that 33% for the phosphorus reduction. So this practice is actually probably a little bit more popular as you head east in the Great Lakes Basin, so the Lake Erie Basin, so in Ohio. We really see a lot more drainage water management going in, and also you have a little bit more flatter landscapes. I know everybody always claims Iowa's really flat, but it's not quite as flat as what people think. Here you can see what that tile system looks like. So it's different from that conventional system where you might just run your laterals up and down a slope. We actually turn that 90 degrees and you run along the contour lines. So that's why it looks a little funky like this, how they run that pattern. But GPS systems, that's a lot easier for the tile guys to be able, tile contractors, to go out there and install. They might not like it as well because they're not just running long lengths of lateral, and there's a lot more connections that end up needing to be made. But it does offer that client that potential to manage that water system in the future. And so we're really trying to promote this practice with the drainage contractors themselves. Here's a map that NRCS put out. I think this was in 2012. But basically, the darker the blue color here is where there's better areas for that drainage water management. So maybe some of your service zones, you find your county, and you can see, right here, north central Iowa, obviously on the Des Moines lobe, that's where we have the highest incident of where these drainage water management can take place. Southern, southwest Iowa is hillier. Obviously, that's a little bit lower areas of where we'd find suitable acres. But in Iowa overall, they estimate there's over 4 million acres that would be suitable for drainage water management. Another benefit of drainage water management that sometimes gets lost is increasing soil carbon. And that sounds a little, I guess, a little odd to hear, but if you think about it, we're reducing how many times that water is raising and lowering there, and so it reduces oxidation. And if we hold water back to make it anaerobic, we're not going to be losing that carbon from that soil profile, so actually we can build that carbon resource back up. And there have been reports of yield increases with drainage water management. It really takes the right season to get that, so where we have maybe enough rain in the spring that you hold that water back early enough and then have that water deficient summer, that's when we see that yield bump from drainage water management. Moving on to bioreactors. So bioreactors is another edge of field practice where we tap into that field tile and we divert a portion of that flow to an underground bed of wood chips. So those wood chips are really just that carbon source that spurs denitrification. So microbes colonize the wood chips, and then they use that nitrate for respiration to process that carbon, and so it removes nitrogen through as N2 gas, so it just releases it back to the atmosphere. Bioreactors are a nice practice in that they fit in just about any landscape position, and so if you have a filter strip like right here, you can see we have that drainage main. We tap into it with a control structure, introduce it to the wood chips. And then we have another collection tile at the bottom end where we reintroduce it back to that existing main. And so that's where we have the bioreactor, running perpendicular to the stream. If you don't have maybe that 100-foot filter strip width to work with to make that work, you can actually just turn that sideways and cut a new outlet into the stream, so then you have to be 20 feet back from the stream typically. Also, we're finding out that we have more farmers interested in putting these along hedgerows, along true edge of fields. We know there's not a stream outlet on every field that's tiled, and so actually back up further in the landscape position, we find that farmers are interested in putting these in next to fence rows, tucking them in. It's a relatively small footprint, 100 feet by about 20 feet is generally about the size of a typical bioreactor.
What kind of acres can you treat?
Yeah, good question. So these are more the smaller scale, again, 30 to 100 acre drainages. They are looking at systems slightly larger, maybe getting up to that 250 acre drainages, those 12 to 18 inch pipes. Those are a little bit more experimental right now about how well they'll work. I will say with bioreactors, it's important to know that you have consistent flow from that field tile. It is a significant investment, about $8,000 to $12,000 per bioreactor. Plenty of financial assistance available, and you can probably get almost 100% paid for right now in the state of Iowa as an early adopter to it. But the practice will last longer if it's on a field tile that drains more consistently and longer throughout the season. If it goes through extended periods of being dry, actually that gets that oxygen back down into those wood chips, and it really just chews up that carbon, and that carbon's not going towards denitrification at that point. And also, I'd also recommend making sure that tile is running hot nitrogen. If you can do a test, the strip test, or send it to a lab and look at that water quality sample. If it's less than 10 parts per million, it might not be the best option for a bioreactor. It might not be worth that investment to put it there. But if it's higher than that, 15 to 25 range, maybe that's the better location for these bioreactors. The wood chips that we use, it really doesn't matter what kind of chip, as long as it's actually a chip. They don't want the shredded material, so this is the first one that went in. And you can see here, actually along the edges, we had more of a shred. This is before there's any standard in place. This is a bioreactor that went in Greene County in 2008. This is kind of the original field scale bioreactor that the Iowa Soybean Association did. I was a part of this install. But these first chips we got actually from a municipal pile. I think there was a big ice storm that previous winter. I think 07, 08 winter was a really big ice storm in Perry, and so they had a huge pile of shredded chips available, and we were doing this under construction, so it made sense that, yep, we can get them in there. Actually, we had just a dump truck to haul these back and forth, which I don't recommend. I really recommend having these semi-trucks with a walking floor bed for it, because the dump truck, all the shredded material just got stuck in the backside of the dump after they lifted it up, so it's kind of a mess to get them out there. But I will say, I wasn't the one doing the planning for this, and so after they get all the shredded material out there that they could, they realized that they're going to be about 100 yards short of filling the hole up with the wood chips. And so they were scrambling because they had a big a press day the next day, because this was the first ones that went in the state. And so actually my boss at the time, Roger Wolf, he was driving back to Urbandale to the office, and he saw this this tree company out in a field clearing something around Urbandale for development, and they had a chipper out there on site. They're chipping it up, so he drove out in the field and knocked on the guy's door. Like, hey, what are you doing with these chips? Can you haul them up to Grand Junction for us? And the guy said, sure, for $1,200 or something, whatever it was. But he backed right. It was great. They backed right up, and actually from them we started hitting those guys up for more sources of wood chips. The longer the bioreactor is, the more retention time that water is going to be interacting with those wood chips. How wide the bioreactor is tells us how much that peak flow of that field tile that it would treat. So we replaced the wood chips. They're actually working on a practice standard right now to help pay for replacement costs. This is one of the questions I usually get when I go out, like, well, what happens after 10 to 15 years? And I never have a good answer to that. I'm like, well, I'm sure NRCS will probably have a standard in place by that time to pay for wood chip replacement, and then 10 years goes by a lot quicker than you think. I've come to find out. But now they're actually, it's going to be a practice standard in place, I think, the next year or two to help pay for those wood chip replacements. Yeah.
Any idea how much the water comes from? Did it all come from the pattern tile, or did it come from intakes?
Yeah, so this
Sorry,
field
could
did
you
have an
repeat
intake on it.
Could you repeat the question?
Oh, the question was how much of the water came from the pattern tiling system itself versus surface intakes. And so generally now in the standard, they don't want surface intakes on these systems for bioreactor. You can do it if there's a surface intake, but they'd recommend doing a water quality inlet instead of just a straight up surface intake before you do it. So you don't want sediment to move in and clog up the wood chips and keep that water from moving in and out. So that's one of the reasons why this one was sized a little bit smaller than what you typically see a bioreactor on a 12-inch line. They actually sized it after an 8-inch tile because they figured, well, we don't really need to treat the nitrogen, because there's not a lot of nitrogen in surface water that's coming down those surface intakes generally, especially not compared to the nitrate that you see coming from that subsurface drainage.
Keegan, what size chunks of the chip? Is bigger chunks better or smaller chunks?
Smaller chunks are probably better, so it's a trade-off between the bigger the chip, the more water you can push through it, so it'll flow faster through it. But the smaller the chip you have, the more surface area to volume ratio for that water bugs to colonize on. So typically about 1 to 2 inch chips is what it is, and they're all flatter. They're not 2 inches thick, but maybe 2 inches long and ½ inch wide or so.
So bigger chips would last longer in there for
Yeah, we'd probably see a lower
efficiency.
reduction rate, but they might last longer. So I mean, you can kind of twist and turn some knobs on it, but from this 1 to 2 inch chip size, they see pretty good performance on it, and they think 10 to 15 years. And like I said, the longer you keep that saturated, the longer the practice is going to last. Actually, the original bioreactors, they used to dig the floor of the chamber itself 1 foot below the tile line, so they'd always have that wetted zone to keep it saturated. But then there's some other issues. You don't want to keep that water getting stagnant. You can have some other issues happening. That's when you really get that rotten egg smell coming out of it. So now they raise that floor to be equal with the flow line with that field tile, so we can always drain the water out. And that's the trade-off, because then we're going to shorten the lifespan. Originally, they thought they could get 20 years out of a bioreactor.
What do you do with the chips after you get them out?
So this one we were just going to incorporate into the field. It's really not that big of a land impact area. Actually, what we ended up having to do, this was, went in 08 when farm prices were really good. So the farmer that was doing this was building a new house at the time, and he took a lot of the soil that we removed from here and put it by his new house for some topsoil. And so actually, you can tell when these things degrade, there's a little bit of indentation, and we didn't mound the soil on this original one. We leveled it off, and so we needed some more fill material actually. So we just put the new wood chips down, put the geofabric on it, and then put those old wood chips over the top, and then the soil over the top, just so we can have it mounded this time around. Yeah, I think just incorporate it into the field.
So your liner's more fabric? I mean, it looks plastic in the picture. The bottom is?
Yeah, so actually the bottom is a plastic liner, and that's just to keep water from moving in and out. I kind of argue if that's really needed or not, but it's relatively low cost, a couple $100 to get a plastic liner in place on these. So if it's $10,000, it gives you a little bit of assurance they're not going to lose water out the bottom end of these things. I guess that's fine. It's a tight soil, like a clay soil. Once you get down there, it's really not needed because you're just going to lose such a low amount of water. But over the top of the wood chips themselves, in between the wood chips and actually the next slide, there's a geofabric. So here's plastic on the side. This is a geofabric, geotextile fabric. And so that allows water to move through it, but it keeps that soil particles from moving into the wood chips. So bioreactors in the nutrient reduction strategy have listed as about a 42% load reduction. That might be a little bit on the high side in my opinion. 20 to 40% is probably what I give for this practice on a given year. If we have rains that are nice and well distributed that everybody likes, you're going to get 40 to maybe 60% load reduction from a bioreactor. But if it's been rainfall, like we've seen the last 4 or 5 years, where we get these really heavy, intense rainfalls, it seems like it all comes in 3 weeks and quits raining on us. That's when it's a little bit less effective, because we do bypass excess water just so we're not backing water up into the field. The next practice, I just wanted to give a plug to these multi-purpose oxbows. So these actually aren't in the nutrient reduction strategy yet. It's not on the 4R Plus website, but we're working to get these areas included. They almost act like miniature treatment wetlands. So here's an example of an old oxbow scar. So rivers meander over time and go back and forth. And eventually we see areas like this that get cut off from it. and they go through wet and dry cycles. And this is just another diagram showing how that works. So these oxbows end up cutting themselves off over time. They're still connected to the water table, historic oxbows are, but over time they get filled in with sediment, and so it disconnects from the water table, so they might already be wet during the spring of the season, and then they dry out, which is a problem because we get fish that move in there and they can't overwinter or stay there year round. But so there's some thought like, well, we have a lot of these oxbow scars around these river systems. We also have some field tile that may be nearby these oxbows. Like, what if we could combine, a wetland treatment idea with an oxbow restoration? And so they're looking at this, and we've actually had pretty good results from doing this. So here's an example. This one was installed in December of 2012, so that was kind of the height of the drought of 2011, 2012. Actually, the nearby receiving stream didn't even have water in it anymore. But here's just the scar before. This is what it looked like day one of that excavation. We actually had water bubbling up in there, which is a really positive sign. We didn't think there would be any water just because of that drought. But we had a couple field tiles. There's one here. I think there's one maybe behind where this photo was taken at the time. So they were able to monitor and see how well it removed nitrogen. Here's another example over by Cedar Rapids, I believe, of an oxbow that the Nature Conservancy in the University of Iowa did. You can just kind of see the different steps. So here's just that scar. So a lot of these oxbows are remnant areas because they are wet during a certain time of the year, but not year round, so they're usually not row crop. And so there's kind of marginal land, and we think there's something that we could do with these. And so here's during the excavation, and that's what it looks like after water gets back into it. This is that first one that I showed after water came back into it that next spring. And we actually didn't revegetate it at all. It just came in naturally. This was in a cattle pasture. They tried to shape the banks to be friendly enough that maybe cows can get down in there. But we're seeing pretty good results from the nitrogen that was moving in. We actually had monitoring wells to look at groundwater above or below the oxbow. And then we were monitoring the outlet of the oxbow to see what was coming out, and then the nitrogen coming in increment. But we were seeing a 42 to 44% load reduction, which is right in the ballpark of all the other nitrate removal practices at these edge of field scales. So we're pretty excited about that. But the other benefit of these oxbows is a great for habitat. So we find that's a little bit easier to sell sometimes because they multi-purpose to it. And actually in Iowa, we have an endangered fish species, the Topeka shiner. It's just a little minnow species that most people probably wouldn't look twice at, but it is federally endangered. And there's some remnant populations in the Boone River and also in the North Raccoon River. And those also happen to be some of the priority areas in our nutrient reduction strategy. And so we think there's potential to get this practice funded there. And we call it a multi-purpose oxbow because they're not designed for 100% of nitrate reduction. For that purpose, you really want it to be shallow and wide to get that water warmer, more interaction with the oxbow bed itself. But we need to have it deep enough at the same time so when these fish come into it, we're not acting as a trap to these fish. That, they come in there during a spring flood, and then if that water runs out, they'll die. And so we don't want to be installing a bunch of these oxbows to remove nitrogen, then having these fish move in and have a problem there because we're killing off the fish shiners. And also the other advantage of these, since there are an endangered fish species that this would help, there's a lot of other groups interested in helping to get these practices in the ground. There is a practice standard that we think we can install oxbows under the NRCS. It's not specifically for oxbows, but it's for the constructed wetland. And there's enough overlap that I think they've done a couple through that cost share program. It might take a DC that's a little bit creative, I guess, when signing up the practice, but it seems like we've had a little bit of luck with that. I guess one of the research notes, if we're looking at this for nitrate removal practices, it does need to be connected with the tile system. If it's just a floodplain oxbow, and we're kind of relying on that flood pulse, when the stream gets high enough and it's pulling water in, you can remove a little bit of nitrogen that's coming down the stream at that time. That's just such an inconsequential amount, it's probably not worth the investment if you have nitrogen removal in mind. But if we do have field tiles feeding into these things, then it is very worthwhile, probably cost effective.
We were working with a FFA student, and she's using our area for a project, but we built a frog pond for the NRCS, and a little deeper at the one end because I like to fish.
Yep.
And they don't know that. But we did divert the neighbor's tile that went across and dumped into a creek, and now we're bringing that in there, not for water, because the subsurface water rises and lowers in there, but we're diverting that in and holding it in that. And she's been tracking the nitrogen.
Get the results from it yet, or? pretty early yet?
Well, let's put it this way, the nitrogen level in the pond is
Yeah.
but the only way it can get into the creek is to filter through the soils.
Yeah. Yeah, and I mean, anytime you can manage that water somewhere, hold it back, get some retention time there, we're gonna see some of those biological processes take place and start removing it. Yeah, it's a little tricky to monitor for it, just looking at it, take a sample from the tile pipe and then the outlet, because there might be a little dilution that goes on too, because some kinds of groundwater has lower nitrate concentration. But yeah, anytime you can try to hold that water back and give it more time before it reaches the stream, generally we'll see some nitrate reduction come from it. Next practice, the saturated buffer. So this is one of the newer practices, even though it's probably been around for almost 10 years now too. But this practice, I think, really makes a lot of sense, and I think farmers are going to be really attracted to it because it has a little bit lower price tag to it than what a bioreactor does. But if you think of our filter strip system that we have in place now, so Iowa does a very good job of getting these grass filters out there, riparian buffer zones, so we're not cropping right up to the field edge. And it does really, really good things for taking that sediment out before it reaches the stream. Sediment-attached nutrients like phosphorus, there's a little bit of total nitrogen that these buffers can process. But as we think of nutrient pathways and how it moves, especially in the state of Iowa in our tile drain landscape, a lot of that nutrients are going right underneath the ground of that buffer system into the stream. And so Tom Eisenhower with Iowa State and Dan James at ARS thought, well, what if we can intercept that field tile with one of these control structures here and then run some distribution pipes just parallel to the stream, allow that water to reintroduce into that soil profile of the buffer. When we get some nitrogen processing going on then, there's a lot of times in those riparian zones, you have really rich organic materials, so there's carbon in that soil available for denitrification. So saturated buffers, if we ever go out on a site visit for somebody that's interested in one of these tile treatment options, usually saturated buffers are the first option we like to consider. They are a little bit more site-specific than the bioreactor, which is more of a generalist type practice. Like I said, bioreactors can fit just about anywhere. With saturated buffers, we do need to have at least 30 feet of perennial vegetation to work with, and that's for federal funding of the practice or state funding. If you're doing it yourself, you can probably get by with 15 feet if you really wanted to. But we need to have that soil organic matter that's there, so that nice dark black soil. In Iowa, that's typically never an issue when we're looking at these sites. That's usually not the limiting factor on it. Usually one of the bigger limiting factors is to make sure that there's no sand lenses or gravel layers next to the stream. So if you get next to these larger river systems where that river's meandered back and forth over the years, that's where you have those gravel deposits a lot of time. And that just bypasses treatment basically, all the water just flushes out there before there's a chance for denitrification to take place. So when we go out and look for sites on these, we refer back to the web soil survey, and if that tells us it's probably not any sand or gravel, we go out there. But you do need to take some soil probes just to make sure. You might be able to get by if it's just a small area with a sand lens or gravel layer, some non-perforated pipe in that specific area, and just get perforated pipe on the other side of it to get treatment. Then finally, stable stream banks. Obviously, we're going to be saturating that zone. We don't want to saturate that stream bank face as well, and maybe trade off a water quality problem with dissolved nutrients for pushing soil into the stream by having eroding stream banks at a time. So stable stream banks are also important to have. I will say they did change the standard last year. Originally, it was written so anything over an 8-foot stream bank wouldn't be considered for a saturated buffer. But if we think a lot of our tile drained areas, that's the drainage district world, and how deep are those streams? They're a lot deeper than 8 feet generally, but they have very stable stream banks because they're engineered, and redesigned on a regular interval there when they clean them out. So they typically have, stable stream banks, and so those are areas that we want to be able to get treatment if we could. And so actually, you can go out there, you can show that the stream bank is stable. You can now do the practice in those locations. Once again, we're kind of in that 44% zone, 33%. That was the number that ADMC came up with this year for our year monitoring, but 44% was a number that Tom Eisenhart and Dan Janes came out with from their most recent round of studies here that they published on that in 2018. Once again, there's federal funding for this practice, the NRCS, practice 604. Also, bioreactors and saturated buffers are both involved in the FSA's CLEAR initiative.
Oftentimes along like a field edge where there's a buffer, with all the years of tillage, the field edge will be like lower soil profile than the buffer. Any issues with the water running back towards the field instead of towards the stream because the soil level sometimes is...
So the ideal site would have a little bit of relief coming from the field edge into that filter strip, just because you want to make sure you have kind of head behind it to push that water out towards the stream. You don't want to be pulling water back behind your control structure. You can do it on flatter grounds like that, but I guess the landowner or farmer would have to know that there's probably going to be a little bit more management involved, kind of like similar to drainage water management. They're going to probably remove stop logs 3 to 4 times during the season. If you do have that flatter, if you have a nice slope, this is a flat tile drain session right here, but a lot of these practices work in hillier landscapes if there's tile there too. But those are the ideal sites almost if you have a hillside coming into your riparian zone, because you can set your control structure out there and put your stop logs in place and pretty much forget that it's there, because you're not going to really risk backing water up into the cropping zone at that given time. Well, I was going to mention this FSA, so the CLEAR initiative, the Clean Lakes, Estuaries, and Rivers, that's looking at reducing nitrogen from reaching those areas. So FSA now includes saturated buffers and bioreactors within the CRP program through this CLEAR initiative. And that's actually a pretty big deal because when we first started putting these practices out there on the ground, these are edge of field next to the stream, and so when we think of those areas, these filter strips that are next to the stream, those are all enrolled in a CRP practice right now. And believe it or not, you can't have 2 federal agencies on the same ground. They kind of butt heads. We wanted to put use EQIP dollars out there to put in a saturated buffer or bioreactor, but since it's on CRP ground, you can't have federal and federal payments, even though one's just a payment to get the practice installed, the other one's the annual rental payment. But to get around that now, it is a CRP practice, and it is doable. Finally, I wanted to mention ADMCs. We just wrapped up a big saturated buffer project with the Farm Service Agency over the past year. So actually most of the work was done before I came on board. I just was the one that wrote the report for it. So what they did was they had 7 monitoring sites scattered between Minnesota, Illinois, and Iowa, but they wanted another year of data to kind of validate these saturated buffers being in the CLEAR initiative. But then they also wanted to look at how scalable the practice is in the Midwest and what impact that would have. But just looking at our water quality results from this past year, we saw concentration reductions from anywhere from 40 to almost 100% of the water moving through. Moving on to how much nitrogen was actually removed from those systems, it had quite a range, 10 to 194 pounds were removed. So here's just the 7 different sites and how much they removed. So Iowa 3 was kind of a weird year on it. It was in an area where the rains missed it early in the season, so I don't know if people remember, it was a little bit drier going into the summer time in parts of, I think it's East Central Iowa. And so this tile actually wasn't flowing during the spring, but then they got really big rain, and so it flowed, and there'd be bypass going on at the same time, so we didn't treat as much water as it wanted to on that one. So that one was a little bit lower at 10 pounds. Also, this Minnesota 2, I think was a good lesson in that the water table was just always historically too high in that area, so we couldn't actually push water from that tile system out of that soil profile because that water table was already there. So that stream depth wasn't very deep. So I think these deeper streams will probably get a little bit more treatment with saturated buffers. But looking at our installation costs, only about $3,600 on average for a saturated buffer, and it probably can be done even maybe a little bit cheaper. So we really think this is a practice that farmers can get behind just because it's a relatively inexpensive practice, and the long-term management of these is very minimal. Like I mentioned, if we have those hill slopes coming in, you don't even really have to change your stop log settings throughout the year. But as long as that filter strip's in place and that vegetation's maintained, the saturated buffer is going to keep on working. And looking at about 20 site years worth of data collected over those 7 sites, we figure we can get about $1.22 per pound of N removed out of the saturated buffers, which is a very cost-effective method of removing nitrogen. Here's just a look at some of the practices that when we think of dollars per pound removed. So cover crops came out high in this one. That's because the numbers that they use, this is kind of the original numbers behind the nutrient reduction strategy, where they found there was a yield drag. And so that yield drag was incorporated into that cost. But all these edge of field, these structural practices are very, relatively inexpensive to remove nitrogen, generally less than $2 per pound of N removed. We also look at these saturated buffers as a way for FSA to enhance their current buffers that they have out there in place. They've already invested millions upon millions of dollars in these buffer strips. We think they can make an additional investment, but basically, if we look at dollars per pound removed, they're not very efficient at removing nitrogen right now because there's just not a lot of surface nitrogen moving through the system. So that was around $16, and then you get the CP22, you got the woody species in there, some more expensive buffers, that's $44 per pound of N removed. But if we look at that footprint and enhance it with the saturated buffer, it drops that price dramatically. And so it makes it about 6 to 10 times more cost effective while removing 13 times the amount of nitrogen from the system. So next we actually contracted with the University of Illinois to look at, how many sites within the Midwest do we think are suitable for the saturated buffers, meeting those conditions, having that organic material, being next to a stream that's not too large or not having that sand layer there, then also a tile drained area as well. So going through that practice, they figured in these 11 states, there's about 23,000 stream miles, so you double that for stream bank miles, that would be suitable for a saturated buffer. That comes out to about 250 to 360,000 sites throughout the upper Midwest. And just breaking that down on a state-by-state basis, Iowa has the most sites, which makes sense because it's probably one of the more intensely drained landscapes that we have. But Iowa and Illinois have nearly 100,000 sites available to them. And we're looking at how much nitrogen can we remove from those tile-drained areas. We can see we can get a significant amount of nitrogen removed by implementing these things to scale. But Midwest-wide, that's about 9.5 million acres that has the potential to be treated with a saturated buffer. That's 22% of the overall amount of drainage acres in the Midwest, and that's looking at about 22 to 43,000 tons of N can be removed, depending on what numbers and how efficient you think these saturated buffers are going to work. And overall, that's about 5 to 10% of the overall nitrogen load coming from the tile drain acres in the Midwest. And if we're looking at the actual N load delivered to the Gulf of Mexico, that's about a 2 to 5% reduction in the N load delivered to the Gulf. Just getting down into the state of Iowa, up to 100,000 potential sites. That's 13,000 miles of saturated buffers. That's treating about 20% of our tile drain areas, including 5 to 9% of the nitrogen, which is very, very effective. We touched upon this a little bit in the previous session, but Iowa has a lot of financial assistance available to it for these practices right now. The big federal ones are the FSA, the CLEAR initiative through CRP, and then also through EQIP. But there's a lot of RCPP practices going on. The National Water Quality Initiative practice is going on in the state as well. IDALS has done a great job of funding these practices and really trying to get them off the ground. I think you heard Secretary Nag mention this morning that I think they're going to make an even bigger investment in these edge of field structural practices moving forward with some additional funding from the water quality bill that got passed last year. And so the time is right, I guess, for people that are interested in putting these in. You can probably get about 100% of these practices paid for. Pork producers do have a pot of money available that they let IDALS manage, but if you're a pork producer that's interested in one of these practices, there's some funding available. If you go to IDALS and ask and request it, that would make the producer whole for putting this practice in, so it would come at no cost. You can match up state and federal funding programs. Additional government programs. There's a few more hoops to jump through to make sure everything's correct. So it might take a little bit longer to get the practice in the ground, but that's an avenue that you can take to get to 100% cost share. So there's looking at the state areas of emphasis. So these are the emphasis watersheds, the Huck 8s that were selected for the nutrient reduction strategy, and these Huck 12s are the areas where there is a dedicated project, WQI project going on right now. There's excellent funding and technical assistance available in all of these watersheds. If you have a client that's here, working here, you have a very good chance of getting 100% funded. Also, the Iowa Flood Center at the University of Iowa has HUD money available to it right now, looking at flood reduction and flood control practices, and they actually are reviewing saturated buffers and bioreactors as being able to do this as you manage the water. So in these watersheds, these highlighted watersheds, there's funding available for these practices through the HUD initiative. The National WQI is kind of a handful of these smaller Huck 12, smaller watersheds throughout the state that has special dedicated funding. Here's the RCPP program. So there's a handful of these out there. You'll notice it overlap with the WQI watersheds by quite a bit. And RCPP, I think, is coming to an end. They've been around for a few years already, and they've spent quite a few of their program dollars, but there are additional dollars in place there. MRBI is a program that started probably early 2010s, and they're re-upping the MRBI program, and actually MRBI really got bioreactors on the ground. In the first place, I think we were able to install about 6 to 7 bioreactors in this area through MRBI. That's an additional NRCS project funding. Another RCPP project through Charles City has specialized funding. And then the driftless area, you can also get specialized funding for these edge of field practices. But with that, I'll take any questions anybody has. Yeah.
Do you think that when you get heavy rains and the water pools in different spots in the field, are you getting more leaching of nitrogen where that water pools or on the highway? Or do you know if there's a difference?
Well, when it pools, you actually get some denitrification in there too, since it creates an anaerobic condition, and so they're using that nitrate for respiration just like they do in the bioreactor. And so
if you don't have water in the high ground, it all runs to low ground. More of that water has to go down. Some of it goes up. Is more of the nitrogen coming from that water just washing through the soil and absorbing the nitrogen with it? And on the high ground where you don't have as much water going down into the ground?
yeah, so once that nitrate or nitrogen gets mineralized, then it's water soluble, and it gets picked up when that water's moving through the system. Yeah.
Would it make more sense than that more of your nitrogen in the water is coming from that perhaps low ground?
I'd say it's probably pretty, wherever that tile is picking up the most water is where that nitrogen is going to be coming from, I would say.
The more of it that's going through is pulling.
Yeah.
I guess I'll ask one. So if, a farmer, somebody advises is interested in one of these practices in particular, can they contact you guys first, or where would you kind of say is the first place to start?
They can contact us, and that'd be a good start. But I always say go into that service center, your county service center first to see. Not every service center knows about all these practices yet because they are relatively new and a little bit different way to think about how to manage these. But they should know the programs that are available and have technical assistance for you. Shane Wolf, IDOLS, he's a new edge of field coordinator. I'd recommend contacting him. The state of Iowa has done really good things about trying to get these practices out there. And they kind of joked before they're trying to give them away. And so I think Shane would appreciate it if you contact him too, because he would love to see more of these going out there.
What's the hydrology in those saturated buffers? Is it wet all the way to the surface most of the time, or?
Not typically. So, they want to. It depends if you have that organic matter all the way down to that depth tile. You don't have to pull that water too high up. Originally when they wrote these, they managed the water within a couple feet of the soil surface, but that was because they had a nice little side coming down behind it, so they didn't really have to worry about ponding zones behind it. But they generally don't want to manage it that high, and so generally you really can't tell too much.
So what percent of the water goes into the soil versus what just goes out the outlet?
It varies on a year-to-year basis, but 30 to 50% is kind of the number I've heard tossed around.
So there's that much flow through the soil into the stream bed?
Yeah, I mean, during base flow conditions, you can generally get most of it. So the distribution lines, they try to get, 500 to 1,000 feet of distribution line for the saturated buffer. The standard's written kind of nicely that they don't have, so bioreactors, that has to be designed to 15% of the peak flow from that main. So that's how those are sized. With saturated buffers, they got around that, which is nice because then you can be more concerned just about how much nitrogen you're pulling out instead of percentage.
In heavy, it seems like from Minnesota, we get heavier rains, everybody has probably. If you never had any lateral movement of rainwater, and it always stayed where it fell, what would that do to your air conditioner?
Oh, that's a good question. I guess I'd have to think about that one a little bit longer.
So if it rained, it always went vertical instead of, you always have a lot of it runs on tracks and stuff. So if it always went vertical into your seepage panel, whatever, it went through the soil profiles, and it stayed there for the crop to use, and then any of it that went to the low ground, but it never went to the low ground, it always just stayed and went vertical. What would it do to your?
So you mean never move across the surface?
Yep.
Or, yeah, I was thinking of lateral subsurface flow. The more water that's moving down into that profile, the more chances it has to pick up nutrients, I would say. And
But if it went on an even basis, so you never had large amounts going in these spots, and just whatever Mother Nature gave you, it stayed in the profile, whatever it could, and whatever went through would go through, of course. But if you never had it, large amounts of water, on my farm, it runs to low ground, it runs to our.
Yeah.
But if that never happened, what would happen to your theory of nitrogen?
I mean, I still think we would see that nitrogen moving just because it's that soluble nutrient, and so any of the water that's moving down to that soil profile will be picking the nitrogen up, and we would need to be able to move that water off, in those flatter landscapes where you get a higher percentage of water moving down to the profile. That's why we have the pattern tile systems out there just to pull that water out because it doesn't have a real great surface draining component
Right,
to
but
it.
as the crop used water and stayed consistent across the whole quarter section,
Yeah.
you would think you'd have less water that's going to get to that.
Possibly, but it's just a matter of when it falls, I guess. It's that gravitational water that we're pulling off of that tile system. So
Looks like from your data, we're paying about $1 to $10 a pound to control nitrogen that we paid 30 cents to put on. Is there a listing somewhere of the cost benefit and so forth of these practices to get beyond subsidy? And how, is there a study of that would help the adoption along with it?
yeah, so there's a couple things. Like nutrient trading is an idea that gets tossed around quite a bit. I haven't seen a real successful nutrient trading program installed yet, but that'd be something working with municipalities that point sources that are permitted that need to remove so much.
How are those numbers determined on dollars per pound then?
Yeah, so they look at the life expectancy of the practice plus the maintenance over that life expectancy to add in, and then just how much nitrogen it's removed on an annual basis. So I think it was either 40 to 50 years life expectancy for it. The bioreactors, I think they actually had the wood chips recharge at 20-year interval. They probably should change that to 10 to 15 on it. I mean, that's going to change it a little bit, bump it up probably another $1 or so on that end, but I think they use like a 4% discounted rate on it then to pay for it up front. So that's why these structural practices a lot of times bring that a little bit lower because it's not an annual payment. You pay for it once up front and then it's there.
Okay, I don't want to hold everybody up for lunch. I don't know if we have time for maybe one more question, and then that might be our time. Or maybe have to go. Thanks so much.